Hi everyone, this is Purnima Mahalingam and you're watching video lecture series on solar and wind energy systems. In last previous two classes, we have discussed about the power electronics in wind energy systems and what are the generator topologies we are used. In this video, we are going to discuss about the converter control strategies in wind and generator topologies. In this, power converters are enabling optimized energy captures from variable wind and they are critical for stability integrations of wind power into national grid. And global wind power capturing reaches on 906 gigawatts in 2022 is highlighting their importance. These are the introduction about this topic. Come, let's go to the video. Here, first one is what is dominating wind generator topologies. What are the wind generator topologies? We have already seen the double effect induction generator and permanent magnet synchronous generator. So in double effect induction generators, that gearbox driven and rotor connected to partial scale converter, that is 20 to 30% of rated power, and allows for various speed operation. That is about, we know that plus or minus 30% of synchronous speed. In permanent magnet synchronous generator is of a direct drive, that is gearless and full converter scales. We have seen that 100% rated power and high efficiency and low maintenance than the gear systems. So both the generators requires advanced power converters for grid connecting and optimize performance. Both the converters, generators are needed, the power electronics converters. Now, here comes roles of power converters. So what are the main roles of power converters functions? So the converter variable generated AC to stabilized grid compiled DAC. So first we need for convert the AC to AC, that is variable AC to fixed AC. Then next one is components. So typically back-to-back voltage source converters with the DC link is important. Back-to-back voltage source converters and DC link and machine side converters and grid side converters. So we need machine side converters and grid side converters, the main thing. And next one is benefits. What are the main benefits? It's a maximum power point tracking, which is active and reactive power controllers and fault detect right through technology capability. These functions ensure the efficiency, energy yield and grid stability. These are the main role of power electronics converters. Now coming to grid uh, here now coming to the DFIG control strategies. What is DFIG control strategies? Is in rotor side controller. So control generates an active and reactive power output and uses vector control method with flux and voltage and voltage orientations and enable maximum power point tracking by adjusting the rotor sides. Okay, next one is grid side controller. Grid side converter is controls DC link voltage. It's control DC link voltage and manage reactive power exchange with the grid and utilize vector control for grid connectors. So these strategies are the DFIG control strategies. Okay. The next one is PMSG control strategies. PMSG controls the machine side converters and grid side converters. We have machine side and grid side converters. And machine side is a control strategy, torque, speed, and converting variable AC to DC and uses rotor flux orientation vectors control for decoupling torque, flux, etc. and implementing MPPT and direct torque control for fast response. Okay. Now coming to the grid side control is regulated DC link voltages and delivering active and reactive power to the grid and utilize grid voltage oriented vector control and provide full active and reactive power control and enhancing grid stability. These are the two main control strategies. One is DFIG control, next one is PMSG control. So these robust control strategies maximize the efficiency and grid support for PMSG wind turbine. Here comes to then an advanced control objectives. First one is maximum power point. First one is maximum power point tracking. So here the algorithms like perturb and observes or optimize torque control and increase annual energy production by 15 to 20%. The first one is maximum power point control. So next one is fault read through control. The next one is fault read through control. So here the maintaining so maintains connections during voltage sag, LVRT, as well HVRT, and injects reactive current to support the grid voltage during the fault. So here the next thing is fault reduction. The next one is grid code compiler. Next one is grid code compiler, and this grid code compiler is meeting annual and regional, national and regional requirements for active power, reactive power, voltage, and frequency supports. These three are the advanced control objectives, and these advanced objectives ensures reliable, efficient integrations of wind power in modern grid technologies. Okay. Here comes the future trends and challenges. Here come what are the future trends and challenges. It is weak grid operations. So develop robust control for grid with low inertia and high impedance, and grid forming capability. So converters acting as a voltage source and enhancing grid stability. Okay. The next one is modern predictive control. There is a offer better dynamic performance and constraints handlings, and cyber security. This is very important. Cyber security, protecting converter control system from cyber threats, and AI and machine learning. So this is the current trends. This is the future research. So optimize control and fault detection. Optimize control and fault detections. So these are the challenges is vital for the future of wind turbine. So these are the future trends and challenges we are going to face in upcoming years. And these are the thing. So next, coming to the conclusions for this. So here we are concluding with the fundamental roles. What is the fundamental role here? This power converter controls is fundamental to modern wind energy systems. We know that. And the energy conservation is enabling energy efficient conversions and robust grid integrations. And the next one is meeting demands. So we have meeting that is crucial for meeting strategies, grid code, and future energy demands, sorry, and driving transients. So innovation control will drive wind power's role in global energy transactions. These four things is main important for concluding, and these systems are pivoted for a sustainable energy futures. Okay, thank you so much for watching these videos, and we'll meet another topic. Thank you so much.